I think.
Okay. I have changed a little bit the title because this was misleading. So I will talk about embedded mobile machine networks in some details. We have seen a lot of generic things like functional safety, cybersecurity, energy management. And now we're going deep into the machine, which is attached or mounted on top of any vehicle for different applications. And I will focus on firefighting equipment in this presentation, but I still will introduce first the body application unit subnetworks, and then also will provide information about equipment for municipal vehicles as well as for agriculture implement subnetworks and other embedded subnetworks. As we have heard in my first presentation, and in the meantime, you might be familiar with the ISO 25200 standard, which is based on the DIN 4630 standard, which describe or specifying the mobile machine integration network. This is also sometimes called bodybuilder network. This comprises body application units. This could be a crane, a tail lift, this could be anything. As well as fleet management units and telematic gateway units, and of course, which is very important, the in-vehicle gateway unit to communicate with the embedded or deeply embedded in-vehicle networks. Some of those body application units use a standardized embedded CAN-open-based subnetwork. We have some of them standardized. One of them is for firefighting equipment in DIN 14700, which has been released in March of this year after a work of 4 years to specify it and to improve it. And I will discuss what are the improvements to the before specified FireCAN, which was also based on CAN-open but was not really CAN-open, but this has been changed. I also will talk a little bit about the refuse collecting equipment, which is standardized in EN 16815 or in CiA 4422. Other CAN-open based embedded networks for machines use a generic and specific CiA profile specification, as Rainer and all the others have shown. So let's still have a look to the architecture that you understand where we are. We are not in the in-vehicle network anymore. We are not in the DIN 4630 network, which could be based on J939 or CAN-open. We are now looking to what is embedded in the body application units. It's called body application unit subnetwork. And there we can add, of course, a lot of different additional devices, and most of the users of such standardized body application subnetworks, they want to buy off-the-shelf products and to integrate them easily into these BAU subnetworks. Today we have available in DIN 4630 the interfaces for container units, for firefighting units. You can see this in DIN 14704. Heating and refrigerating units, refuse collecting units, you have to look to the EN standard or CiA 422, tail lifts, tipper units, and vehicle-mounted crane units. And this document is going to be extended so that we can address also other body applications. But now we look to what the firefighting people have done. It's not only firefighting equipment. This might be too short. There are other rescue vehicles, including ambulances and civil defense trucks, which uses similar equipment in the embedded networks. And the most common unit is the warning signal unit. And I was yesterday with one of the supplier of this, and they are quite happy to have one single standard and can now have just one interface for all of the different kinds of vehicles. And just by means of configuration, you make this then an ambulance, you make it a firefighting truck, you can also mount this on some civil trucks for defense. Let's have a look into the details of the DIN 14700 standard, just as an example for other bodybuilder networks or embedded bodybuilder networks. You see that here we have a host controller connected to the DIN 14630 or ISO 25200 in the future network. It could be J9039 based, or it could be CANopen based. In this case, it is J9039 based with an in-vehicle gateway unit standardized in DIN 14704. The embedded bodybuilder network comprises different devices. An example is the frequency inverter unit. Then we have the light mast unit, we have the power extinguish unit, etc. There are a lot of different units which have been standardized with their interfaces based on CANopen. When we started this approach, we wanted to harmonize the specification, which was done before in different documents. But this was a nightmare, because then the documents changes at different times, and how to synchronize the release of those documents is quite complicated, let's say in these words. And the benefit of the monolithic document is that it also was published in English language now, so that we can give it to suppliers all over the world, and not only in Germany, because before it was just written in German language. In order to enable the use of off-the-shelf commercial or open source CANopen protocol stacks, all necessary object dictionary entries have been specified. In the previous and the legacy version, there was just a subset specified, so that you can't make really, or you can't really use generic CANopen tools as well as for analyzing purposes or for developing purposes. The implementation of PDO mapping parameters is still optional in order to be backwards compatible. So this is why we have some restrictions in the functionality of CANopen. The trade-off of that PDO configuration option is it's limited and cannot adapt it to special use cases. This, you have to live with that. The implementation of the complete CANopen dictionary is recommended for new designs in order to use off-the-shelf CANopen tools. The specified PDOs use all 8 bytes of the CAN data field. Filling not needed bits and bytes with dummy parameters is needed, of course. Just going into some details that you see how huge the standardization effort is, which we have taken. We have specified up to 5 battery charger units, up to 4 frequency inverter units, up to 2 light mast units, etc. And last but not least, we have also 6 warning signal units. These are the blue lights on top of the vehicles. The host controller and the different shown firefighting units use uniquely assigned node IDs. And we have also 8 node IDs reserved for manufacturer-specific purposes, because might be that there is a new unit or a dedicated unit needed for some special purposes, which we have not covered by the current specification. Most of you will be quite familiar with CANopen, so you need a normal CANopen protocol stack. And there's one exception, that you have to provide also the error service. This is a dedicated PDO. I will come to that in one of the next slides. We have the normal object dictionary, and we have the application software, and you can access each of the parameters in the object dictionary by means of a unique 16-bit index and an 8-bit subindex. So this is nothing new. This is normal CANopen as you know it. What we have done is that we have specified all different parameters. Now, just here as an example, here you see the LMU light mast unit control parameter, which is a 2-bit value in this case. And you see that we have then this entry description of this. So we have the value range for us to stop something. There's all the way 0, The start is always 0, 1, and if there's an error indicated, then it's 1, 0, and we have not no action or not available, then we have a 1, 1 in as a value specified. This means we follow the CiA J939 approach with an integrated error information if something is not okay. The default values for the host controller is not applicable because the host controller starts its software and initialize itself, and then it provides the information. For the light mast unit, the default value is 1, 1, meaning do nothing, waiting on the host controller what the command is. The parameters are all 8-bit parameters, and they are mapped into the PDOs. In this case, it's TPDO2 and RPDO2 for protocol and parameter mapping. And the producer is always the host controller, and the consumer in this case could be the warning signal unit, the light mast unit 1, and the light mast unit 2. You see that all 8 bytes are used, and I have just for the light turn right, folding a move down, dummy and dummy and dummy. This means we have still 3 2-bit parameters available for future extension. All these parameters, the mapping parameters are given in the document, as well as the pre-configured communication parameters. So this is nothing new. What is quite different in this approach, and we want to make it as easy as possible for the system designer, that all TPDOs shall be transmitted with a period of 3000 milliseconds. As you may know, this is configurable by the event timer, but in this case, it is fixed. And this starts when the device enters the NMT operational state. There's also an inhibit time assigned of 100 milliseconds, so that means that you not block the bus, but only if there is some time is frozen, so to say. You can't send it within the 100 millisecond. The CAN ID assignment does not follow the predefined connection set. So you can't integrate into the DIN 14700 network any generic CAN open device without configuration. This would lead to some CAN ID collisions. The process parameter received in the RPDOs shall be processed within the event time of the corresponding TPDO. In our case, now 3000 milliseconds. Of course, this is the dedicated application, and water flow and all the others is quite slow compared with high-speed applications. So the PDO communication parameters should be implemented, even if they are fixed, just for maintenance and diagnostic purposes. And then you can use off-the-shelf the CAN open diagnostic or system design tools. Of course, DIN 14700 also specify other CAN open protocols like SDO. This is mandatory, and the host controller shall implement the SDO clients for all connected CAN open devices, and the firefighting units shall implement the corresponding SDO servers, of course. NMT protocol is supported by the host controller, and to start and stop the connected CAN open devices, which are the firefighting units. Heartbeat protocol is also mandatory. Heartbeat producer time is 1 second, and can be used by the NMT manager as a confirmation of its NMT commands, as well as by any CAN open device as an indication of the availability of the heartbeat transmitting CAN open device. Heartbeat consumer time shall be 2 seconds. There is one thing in addition. You shall produce, or all FFUs shall produce, so-called error messages. This is different to the emergency because they provide different content. So to say, a special purpose PDO and the host controller shall consume all error messages from the FFUs. The mapped warning and failure codes are FFU type specific, so the inverter has other warnings and other failure codes than the battery unit, for example. So this is highly standardized, and this makes diagnostic quite easy. The error control is implemented, as I said, as a special PDO message. It has the communication parameters are specified in index 19FF, and the message is transmitted when there is detected a change of value. So when one of the values in the map parameters is changed, then it will be transmitted. The host controller needs to process this information immediately after reception. Immediately is also not very precise, but we hope that this will be not an issue when you have not specified a dedicated time. The error mapping parameters are specified in the index 1BFF, and there's only one process parameter mapped, and this parameter contains the latest warning information. The other list entries can be read by means of SDO service protocols, so that you can read the entire history up to 250 failures or warnings. The benefit for OEMs is the specified interoperability of host controllers and firefighting units simplifies network design and device integration, because you can now buy from different sources functional equivalent devices, and now you can exchange them quite easily, or you can integrate them without any big effort. Of course, they are not 100% interchangeable if they provide different functionality. Also, this can be read by the object dictionary, which functions have been implemented, and then this makes it quite easy to integrate this into the host controller and to communicate with them. Benefits for the suppliers. The firefighting unit suppliers can address a broader market. Besides the firefighting vehicles, DIN 14700 compliant devices can also be used in ambulances and other rescue vehicles. So this could be cranes, this could be a lot of things. So, and another benefit is now you can use standard can open protocol stacks, and you also have the possibility to use generic can open controllers, and just to provide your own software, or you have a software from one of the software vendors offering DIN 14700 functionality. So this is a benefit for both, for the OEMs as well as for the suppliers. What was demanded and not yet achieved is that there is some generic protocol stack available which you can integrate easily into any device. Still, you have to, in the moment, to look for a protocol stack and additional software. Similar approach we have with municipal vehicles, in particular with the refuse collecting vehicles. We have standardized CiA 422 since many years, and it's also internationally standardized in Europe in EN 16815 from 2019. And we are going to update this in the next round of revising these documents. There's another approach for municipal vehicles. They have standardized winter and road service equipment. This is the pre-standard or the pre-standard 15430-1 edition 2. Unfortunately, it is not based on can open at the moment. It uses still 232 links to the different sub body application units or to the different devices, but it is ready because the parameters are described in a way that also can easily be mapped to CanOpen. And if somebody is interested in that, then we can, from CiA, we can provide a document mapping the parameters specified in the EN standard to CAN-open-based networks. So to substitute the serial link by means of a CAN-open network, which is in some applications might be an improvement. Similar, the agriculture implements subnetworks. We see there are a lot of CAN-open applications in the harvesting machines or in the sprayer or in whatever the implement functionality is. Normally they use CAN-open sensors and actuators compliant with the CiA profile specifications like and etc. You have seen them, and Rainer and all the others have mentioned it several times. And CiA is going to start develop for a profile for radar sensors, which are also used in those equipment by next week. And there will be then a harmonization of CAN-open and J939 parameters, and we can have them mappings to CAN-open as well as to J939. And for your information, also other profiles from CiA have already a mapping to J939-21, for example, for the encoders and for include-meters. And we are working on this also for all other profiles. There are also other kind of mobile machines, and they use some subnetworks in more complex machines. And most of them use CAN Classic as a data link layer. Some of them are using CAN-open as high layer protocol, connecting sensors and actuators as well as human machine interfaces to a host controller. Several of them are safety related, meaning that they implement the CAN-open safety protocol and the according profile for the for encoders as well as include-meters or other devices. VDA has started to develop a CAN-based embedded network for a battery management system suitable for forklifts. But this is just the starting point, and we are going to observe this from CiA and to support them and to provide comments to their specification. As I have said, there's also the European standard for winter and road service vehicle equipment, still based on 232 serial links, but with the option to map the specified parameters to CAN-based networks in a second step. And CiA is willing to support this and to help those people to provide a mapping to CAN-open.